starting from there, that's half of the wavelength, and that's full wavelength. So the L, the length of the pipe, will represent the wavelength. Therefore, V is equals to F is equals to V over L. Similarly, we will have third harmonic should have 3 loops, 1, 2 and a half on this side and a half on that side will make it 3. And again, the general form to find F here is normally NV over 2L. So if it's third, it's 3V over 2L. Here we also have, for second one, we have 2V over 2L, 2 and 2 will cancel. That's why we have V over L. The general formula form continues. And for fourth one, we will have 4V over 2L, 4 will cancel with 2, and we have 2 on the numerator. And it's fourth harmonic, so we should have 4 loops, 1, 2, 3, and then we have 4. Remember, every time the end of the pipe on both ends, since it's open, we will have an empty node. Thank you. So again, it is for strings with both and no air columns pipe ends. The general formula for frequency is given by, okay, we're talking about, this is what I was saying, we'll look at it later. So for open pipes and strings, we are going to have, this is the general formula to find frequency, NV over 2L, where our N is 1, 2, 3, and 4. And for closed pipe, we have F is equals to NV over 4L. And in this case, our N is only, it's going to be odd numbers. Then we have speed of a wave in a string. Okay, so a speed of wave is dependent on the tension in the string. Actually, this is a lab kind of thing. We'll try that if we get to meet in the lab. The acceleration, the wave speed increases with increase in tension of the spring. So this is what actually these people, the guitar, you know, you have seen them, people with the guitar tuning the string and other stuff. So they're actually playing with the tension. Okay, the acceleration, the wave speed increases with the increase in tension of the string. Also, the wave speed is inversely dependent on the mass per unit length. So if you have seen a guitar, the mass, I mean the thickness of the string on the guitar, there are 6, and all of them are different. That is what gives the different sound. Okay, the speed or the velocity of sound on this depends on the mass as well. So you will see mass per unit length, and that is here in the formula. You'll see that is mu. Mu represents the mass per unit length, and what it is given as mass divided by the length. Mass in kg and length in meters. Okay, so that is the formula to find velocity. Remember tension, T. If we are hanging something on the mass, the weight of that mass will give the tension in the string. Then comes the beat. Okay, beat actually is the difference between the frequencies that we hear. Okay, it's absolute, so it will not be negative. It's always the bigger minus the smaller one. Beating in is a regular pulsing of loudness of a sound that is heard when 2 sources produce sound of slightly different frequencies. Beat frequency FB is given by, so example is there. If 2 tuning forks of frequency given are sounded, what beat frequency would be heard? So it's always the bigger minus the smaller one, because we're taking the absolute, so it will never be negative. 74 hertz. Some more examples there. String vibrates in its fundamental mode of 50 hertz. So fundamental means where our N is equals to 1. Okay, and string, so we know it's the ends will be what fixed. The string is 50 centimeter long, so that's the length of the string given there. Both ends fixed. Calculate the wavelength. So wavelength, we know when fundamental, your wavelength, you'll see here. You'll see here that your wavelength is equals to 2L. Okay, and your length is 0.5 meters, therefore 2 times 5. So your wavelength for the first fundamental will be 1 meter. Okay, and part B, determine the speed of the wave in the string. Talking about wave, so F is equals to V over 2L, and you make V the subject, you get 50 meters per second. Part C, sketch the first and the second. So first, you know, this is going to be antinode. Node at the ends, and it's 1 loop, so an antinode. Please, whenever we are asked to draw or sketch the harmonics, you need to put N and A denoting antinode and node on the diagrams. I have missed it. Please, whenever you are asked to do it, you have to do that. Second harmonic, there should be 2 loops, and we should have antinodes and nodes at the end. That means these ends will always be fixed. They are not moving. Okay, let's move. And part D says find the frequency for first and second harmonic. We can always say first harmonic, use the formula N, F is equals to NV over 2L, N is 1, and the second harmonic will be N, F is equals to, it's done there, 2 over 2 will cancel, so 100 Hertz. So example 2 is there. This is on the second part where we're talking about tension in the string is there. Uniform string has a mass of 0.3 kg and length of 6, so that will be used to find the mu, and the tension is maintained in the string as shown. So there's a maybe a 2 kg mass hanging that is causing the tension, that is 2 newtons there. Then it says calculate the mass. Okay, let me delete this. It says calculate the speed of the waving string. So to find the wave, we first need to find mu, and mu is given as what? We have done the different formula here. Instead of mu, we have it's L over just, or you can always find this and replace the T over mu. And mu will be what? It's 0.3 divided by 6, and then you'll have 20 divided by the answer square root. It's going to give you 20 meters per second. And after that, part B says sketch the fifth harmonic. Since it's a string, it will have fixed ends. So the 2 ends are fixed. I should be writing N here and N here and N all those. And how many loops are there? Since we're talking about fifth, so there should be 5 loops, 1, 2, 3, 4, and 5. And find the frequency of the fifth harmonic. Formula is F is equals to NV over 2L. So NV over 2L, N is 5 times V we have calculated to be 20 meters per second here, and the length is 6 meters, so 2 times 6, and we get 8 1/3 Hertz as the frequency. Thank you.